Hey guys, welcome to another CNCM lecture. This one's going to be on expected value, and in particular, the linearity of expectation. It was put together by one of our members, Paul Hamrick. Huge thanks to Paul for putting it all together. I'm just narrating over it. So, what is expected value? Well, first of all, a random variable is something that takes on a particular value with given probabilities. So, for example, if you were to roll a dice, your possible outcomes are 1, 2, 3, 4, 5, and 6. And each of those outcomes occur with a probability of 1/6. And if you wanted to find the expected value of this random variable, what you would do is you would consider your possible outcomes and do a kind of weighted average where your weights are the probabilities. So a value of 1 is taken on with a probability of 1/6. So you would do 1 times 1/6, and then you would have an outcome of 2 with probability 1/6. So you would add on 2 times 1/6 and so forth. And if you add all these up, then you get 21/6, which is 3.5. A great thing about expected value is that you have what's called the linearity of expectation. So if you have any n random variables and you want to find the expected value of their sum, it's going to be equal to the sum of their expected values, regardless of whether these variables are independent or not. So regardless of whether the outcome of one variable could affect another one of your variables. So let's illustrate it with an example. Caroline's going to flip 10 fair coins. If she flips n heads, she will be paid n dollars. What's the expected value of her payout? So Caroline's going to be paid $1 for each coin if it turns out as a head. So for each coin, if we set a random variable to have a value of 1 if it lands heads, or 0 if it lands tails, then we want the expected value of the sum of these random variables. And by the linearity of expectation, this turns into the sum of the expected value of these variables. Now, the expected value of any one of these variables is fairly simple to compute. They take on $1 if you, with probability 1/2, and a value of $0 or nothing with probability 1/2 as well, because there's a half chance of flipping heads and a half chance of flipping tails. Let's move on to a slightly harder example. So values A1 to A2013 are chosen independently and at random from the set 1 to 2013. What is the expected number of distinct values in the set A1 to A2013? So to solve this problem, we'll consider every number from 1 to 2013 and individually. So the number 1, we want to find the probability that it shows up in the set A1 to A2013. And to do that, well, we note that A1 takes on a value of 1 with probability 1 out of 2013. So in particular, it does not take on a value of 1 with probability 2012 out of 2013. And if we raise that to the 2013th power, that gives us the probability 1 does not appear in the set at all. So the probability it does appear in the set is 1 minus that. And so that gives us the probability that the number 1 shows up in the set. Now, by the linearity of expectation, if we add up all these probabilities, which are all the same, that will give us the expected number of distinct values in the set. So your answer is simply going to be 2013 times what we had before. So here's an application to one of our past POTDs. that I was not too happy about including, but it's a fairly good application of the linearity of expectation. So how many 6-letter words formed from the letters BDR do not contain the substring BDR? And so the idea here is that we consider any random 6-letter word formed from the 3 letters. And we note that there are 4 consecutive positions of 3 that the substring could appear in. And for each of those possible positions, there's a 1 out of 27 chance that the substring BDR appears in those 3 positions. And since by the linearity of expectation, any 6-letter word has 4 out of 27 instances of the 3 letters. Because there are 4 consecutive positions. So since there are 729 words, we just multiply 729 by 4 out of 27 to get there 108 total instances of the 3 letters. And each letter can only have at most 1 instance, except for the 6-letter word BDR, BDR. So there are 107 words containing the 3 letters, and we subtract that from 729 to get 622 letters that do not have those the substring. Let's move on to an Olympiad application. So in the Duma, there are 1,600 delegates who have formed 78 committees of 80 people each. Prove that one can find 2 committees having no fewer than 4 common members. So to solve this problem, what we're going to do is we're going to try to compute the expected overlap between any 2 committees. And so if we let the number of committees the ith delegate is on be AI, then for each member, we can choose 2 of the committees they're on, and that will be 1 overlap. And in particular, if we choose 2 committees for every single delegate and add all those up, so that's going to give us the summation on the left-hand side. And that will give us the total count of overlap, and we divide by the number of pairs of committees, which is 78 choose 2, to get the expected number of overlap between any 2 committees. And so we can get a lower bound on this number by Jensen's, because the function x choose 2, which equals x squared minus x over 2, is convex. And if we do that, we'll get a lower bound of approximately something that's slightly greater than 3. And so if the expected overlap is slightly greater than 3, that tells us there has to be 2 committees with at least 4 members in common. Let's move on to a more difficult Olympiad problem. A circle is divided into 432 congruent arcs by 432 points. The points are colored with a quarter being red, a quarter being green, a quarter being blue, and a quarter being yellow. Prove that one can choose 3 points of each color in such a way that the 4 triangles formed by the chosen points of the same color are congruent. And the idea to solve this problem is to first let R be the set of all red points. And if we fix any one of the red points, there are 431 possible rotations, of which 108 take that point to a green point, because there are 108 total green points. And so the expected overlap that particular point contributes is going to be 108 over 431. And so by the linearity of expectation, the expected overlap with any rotation of R with G is going to be 108 squared over 431, which is slightly greater than 27. And so that tells us there has to be a specific rotation that yields 28 points in common with G. And then if we take those 28 points and apply a similar rotation argument, we get that there have to be 8 points in common with Y in this second rotation. And finally, if we do this argument one more time, we get that there have to be 3 points in common with Y in the final rotation. And in particular, those 3 points are going to form a triangle, a completely yellow triangle. And now if we go back and undo all the rotations, each of them is going to give a triangle in one of the 4 colors. And since rotations preserve congruence, all these 4 triangles are going to be congruent to each other, but they're all going to be of different colors, which is exactly what we wanted. Let's finish with a final computational example. Suppose 7 boys and 13 girls line up in a row. Let S be the number of places in the row where a boy and a girl are standing next to each other. And the problem gives an example, and we're asked to find the average value of S. So any boy-girl pair has a probability of 2 times 19 over 19 times 20 of standing next to each other, because there are 19 consecutive positions of 2 in the 20-letter string, and it could either be BG or GB, so the numerator becomes 2 times 19, and there are 20 times 19 possibilities for where you place the BG in this B and G in the string. And so that gives us a probability of 1/10. And since there are 91 boy-girl pairs, by the linearity of expectation, we expect that 91 over 10, or 9.1, that there are going to be 9.1 expected occurrences, which gives the answer of A. Here are some 3 fairly advanced Olympiad problems for practice. They all have very nice solutions, and I definitely recommend you try them out. And that's it for this lecture. Please join our Discord server in the link below, and we hope to see you next time.